All right, welcome to The Explainer. Today, we're going to tackle one of the absolute biggest ideas in all of science, gravity. And you're about to find out how a crazy sounding idea from 100 years ago is the reason the smartphone in your pocket actually works. So, it all kicks off with a question that sounds super simple, almost like a riddle for kids, but it's actually incredibly deep. If you're in a vacuum, a feather and a cannonball will fall at the exact same speed. Now, this little fact completely stumped people for centuries, and believe it or not, it set the stage for a total revolution in how we see the universe. For a long, long time, I'm talking 300 years, we thought we had it all figured out, thanks to Sir Isaac Newton. His idea of gravity was basically an invisible force, like a cosmic string, that just instantly pulls things toward each other. And you know what? It worked. It was brilliant, it was elegant, and it predicted the orbits of planets with amazing accuracy. But there was a tiny hidden flaw. And here's the catch: speed. For Newton's theory to be right, gravity had to work instantly, everywhere, all at once. But then along comes Albert Einstein in 1905 with his theory of special relativity, and he basically hits the brakes. He proves there's a universal speed limit, the speed of light, and absolutely nothing can go faster. So, you see the problem. That contradiction meant our whole understanding of gravity, one of the pillars of physics, was just plain wrong. The solution didn't come from some ridiculously complex math, but from a moment of pure insight. It was this flash of genius that Einstein himself called his happiest thought.
He pictured a man falling from a roof. Now, during that fall, the guy would feel completely weightless, right? If he took an apple out of his pocket and let it go, it would just float right there next to him. For that brief moment, it's as if gravity just vanished. And that's when it clicked. The feeling of gravity and the feeling of acceleration are really the same thing.
And this massive idea gets a name, the equivalence principle. It's a really powerful statement, and the best way to get what it means is with a classic thought experiment. Okay, imagine you're in a sealed room, no windows, can't see out. First, the room is just sitting on Earth. You drop a ball, it falls to the floor. Simple. Now, imagine that same room is in a rocket, out in deep space, but it's accelerating upwards at exactly 9.8 meters per second squared. You drop the ball again, and the floor rushes up to meet it. From your point of view, inside that room, the two situations feel absolutely identical. There is no experiment you could possibly do to tell the difference. And look, this isn't just some clever parlor trick. It's one of the most precisely tested ideas in all of physics. Scientists have built these unbelievably sensitive instruments, like this torsion pendulum you see here, to check if maybe, just maybe, different things fall at slightly different rates.
The results are just staggering. These experiments have confirmed the equivalence principle is true to an accuracy of 1 part in a trillion. That's like measuring the distance from the Earth to the sun and being accurate to within the width of a single human hair. It's just dead on.
Okay, so if gravity and acceleration really are equivalent, this is where things start to get really weird. The consequences are totally mind-bending. It means gravity can do things we never, ever thought possible, like bend a beam of light. Let's hop back into our rocket in deep space. So, what would happen if we shined a perfectly straight beam of light from one side to the other, all while the rocket is accelerating up? Let's just follow the logic here. So let's think about this. If you're floating outside, just watching, you'd see the light travel in a perfectly straight line. But for the person inside the rocket, as that beam of light is traveling across, the floor is accelerating up to meet it. So by the time the light gets to the other wall, the wall itself has moved up a bit. To the person inside, it looks like the light actually curved downwards. And right there, that's the power of the equivalence principle. If an observer inside the rocket sees light bend because of acceleration, and acceleration is indistinguishable from gravity, then gravity must bend light too. Gravity isn't some force pulling on the light. It's actually warping the very space that the light is traveling through. But hold on, because it doesn't stop with space. The equivalence principle leads to an even stranger conclusion. Gravity doesn't just bend space. It actually warps the flow of time itself. Let's put two super accurate clocks in our accelerating rocket, one up at the top and one down at the bottom. Now, the clock at the top sends a little light pulse down to the bottom one every single second. But because the rocket is accelerating upwards, the bottom clock is constantly moving into those light pulses, so it receives them just a little bit faster than the top clock sends them. to the clock on the bottom, it looks like the clock on top is ticking faster than it is. And because of the equivalence principle, this has to be true in a gravitational field as well. The stronger the gravity, the slower time passes. And yes, this means right now your head is aging just a tiny, tiny fraction of a second faster than your feet. It's real. Now, I know this all might sound like some bizarre, abstract theory that has nothing to do with our lives. But here's the thing. Without it, a piece of technology you probably use every single day would completely fail. I'm talking about the GPS in your phone. I'm talking about the Global Positioning System, GPS. This whole amazing system is just a network of satellites orbiting Earth, and each one has an insanely precise atomic clock on board. Your phone figures out where you are by comparing the time signals from a few of these satellites. But here's the problem. Time for those satellites is being warped by relativity. You see, you've got two things happening at once. First, because of special relativity, those satellites are moving really fast, so their clocks actually run about 7 microseconds slower each day. But then, because of general relativity, the satellites are way up high in weaker gravity, so their clocks run about 45 microseconds faster each day. So you do the math. The speeding up effect is bigger than the slowing down effect. The end result is that the clocks on GPS satellites get ahead of our clocks down here on Earth by about 38 microseconds every single day. A microsecond is just a millionth of a second. That sounds like nothing, right? But light travels about 300 meters in a single microsecond. So that tiny 38 microsecond error would add up to a positioning error of over 10 kilometers every day. Your GPS would be completely useless. You try to find a coffee shop and it would send you into the next county. So what this all means is that Einstein's happy thought totally rewrote our understanding of the universe. Gravity isn't an invisible force pulling things. It's the effect of mass and energy literally bending and curving the fabric of space-time. The Earth isn't pulling the moon. The Earth has warped space-time around it, and the moon is just following the straightest possible path it can through that curved space. And that is the real legacy of this incredible idea. It just shows that even the most familiar things in our lives can hide secrets that are way deeper and stranger than we could ever imagine. It makes you wonder, doesn't it? What else are we looking at every day without really seeing what's there? Thanks for joining The Explainer.